So this is our work, GoFetch. This is the joint work with Yingchen, Pradyumna, Chris, David, Riccardo, and Daniel. So firstly, let's do a brief recap of timing attacks. Timing attacks leak data due to secret-dependent timing difference. One typical timing difference comes from the cache. Modern processors use the cache to reduce memory access latency. Data in the cache is faster to access than it is in the main memory. By measuring its access latency, we can deduce its location in the memory hierarchy. One simple cache timing attacks vulnerable program could be constructed as a secret-dependent memory access. Depending on the secret value, one memory load to address A could be performed or not. Suppose before this code execution, we flush the entire cache, and after the execution, we time the memory access latency to the address A. Since we flush the cache beforehand, the cache does not contain the data at address A. If the secret is 1, then the branch is taken, and the address A is filled in the cache. In this case, when we time the access latency to the address A, we will hit the cache and it takes less time. If the secret is 0, then the branch is not taken and the data is not loaded by the program. And when we time the access latency, we will miss the cache, load the data from main memory. This takes longer time. From this timing difference, the attacker is able to recover the secret. To defend against timing attacks, cryptographic communities propose constant time programming paradigm as a software solution. To achieve constant time, a program execution time should be independent of its secret. Constant time programming is made up of 3 best practices, namely, the secret cannot influence the control flow, the memory access pattern, or be passed to time variable instruction operands. By following these principles, a cryptographic implementation should be free of any potential timing attacks, and cryptographers should have good sleep at night. In this talk, I'm going to show that these principles are insufficient to block timing attacks on modern processors. More specifically, our discovery related to data memory-dependent prefetchers on Apple M-series CPU shows us that these pieces of hardware can indeed make constant time code non-constant time. Even if one program does not contain any secret-dependent memory access, the data memory-dependent prefetcher will still spit secret-dependent memory requests. As a result, we revive cache timing attacks. The reason is that Apple's DMP can treat any data loaded from memory as address and perform memory access to that address. From the performance perspective, this is great because when the program performs pointer tracing access pattern, DMP can detect the pointer values and preload the next target so that it can help with hiding the memory access latency. However, from the security perspective, let's use a simple constant code as an example. This line of code loads the secret data from a non-secret address. Suppose the secret could be one of 2 distinct pointer values, pointer 1 or pointer 2. These 2 pointers are pointing to 2 different cache lines in the cache. Now, without the DMP, no matter what the secret is, there will be only one memory access to a non-secret address for both pointer values. This makes pointer 1 and pointer 2 indistinguishable over cache timing side channels. However, with the existence of the DMP will further perform memory access to the value returned by the load, the value named secret here. If the secret equals pointer 1, then pointer 1 will be dereferenced by a DMP. If the secret is pointer 2, then pointer 2 will be dereferenced. Dereferencing pointer 1 or pointer 2 will leave different cache states, which are observable to a co-located attacker. This means that the attacker can say what the secret is, pointer 1 or pointer 2. You may have heard Augury before. This was the first work to discover DMP on Apple M1 chips, but it was not able to demonstrate an actual attack. We make 3 main contributions over Augury. First, through comprehensive reverse engineering, we found that the memory access pattern described in Augury is not necessary to activate the DMP. It was for this reason that Augury cannot demonstrate an actual attack. Its understanding of how DMP worked made it impractical to exploit. Next, with our newfound how DMP can activate, we set out to break cryptographic implementations. we still face a major hurdle that DMP is only capable of leaking pointer values. To overcome these limitations, we built a new type of chosen input attack, where the attacker can engineer a secret-dependent pointer in intermediate crypto states and then exploit the DMP to deduce the secret from that. Finally, we built end-to-end key extraction attacks to undermine full constant-time cryptographic implementation, either deployed in the wild or submitted to NIST post-content cryptography standardization. Before we dive into the attack, let's understand the DMP better. Let's firstly recall how the classical hardware prefetcher works. Usually, it takes the previous access address trace as the input and extrapolates the future address to prefetch. For example, the stride prefetchers learns the stride by monitoring programs' stride prefetch, stride access pattern, and when it gains enough confidence, it will start prefetching by the then stride. The prior work algorithm follows the same intuition to reverse engineer Apple's DMP, and is settled down with so-called array of pointer access pattern. It discovered that what DMP prefetch is not only determined by the previous access address trace, but also the content in data memory. But security-critical software does not typically have such an idiosyncratic access pattern, and that is why algorithm is so constrained to conduct an actual attack. From algorithm, we ask the question, is this access pattern really necessary, or does Apple DMP really have a phase of confidence accumulation? The answer is no. Even a single memory load is enough to trigger Apple's DMP. Let me say that again. Potentially, any data loaded from memory is a candidate to be treated as a pointer and dereferenced by a DMP. Meanwhile, not only the pointer fetched by the program, other pointers within the same cache line are also dereferenced by the DMP. The next question is, where does the DMP scan the data to see if it is a pointer? We conduct experiments to move the pointer value around the memory hierarchy, and we found that the DMP only monitors L1 cache fields, at which time it scans the data to see if it looks like a pointer. From this understanding, we further examined how DMP searches for pointer within a cache line. It turns out that it checks each pointer size aligned chunk to see in the cache line. And to successfully dereference a pointer, its target must map to a valid memory region within the process. Beyond these observations, we'll further reverse engineer other features of Apple's DMP. For example, how does DMP avoid redundant dereference when it encounters duplicate point values? Please check out our paper to see those details. The fact that the DMP can only leak pointer value is a significant limitation because usually crypto state looks random. To overcome this limitation, we developed a new type of chosen input attack. The high-level idea is that we can craft an attacker chosen input such that depending on the secret value, an intermediate crypto state could be either pointer or not pointer. Pointer or not pointer will result in distinguishable DMP behaviors, and the attacker can deduce the secret from that. Let's use a concrete example. Suppose our target implementation is an AND operation between chosen input and the secret. The secret could be either 64-bit O1s or O0s. And the attacker's goal is to identify the secret value. Now the attacker says that I'm going to use a valid pointer value as the chosen input. If the secret is O1s, then the intermediate crypto state will still be the pointer. If the secret is O0s, then the crypto state will be masked to be O0s. As a result, by monitoring whether the DMP dereferences these pointers, the attacker can infer whether the secret is O0s, O1s, or O0s. The previous example shows the basic idea, but it assumes a very simple AND operation between the chosen input and the secret. Real crypto implementations are significantly more complex. We conduct crypto analysis and build end-to-end key extraction POCs. Our POCs include OpenSSL Diffie-Hellman key exchange, Ghost RSA decryptions, module lattice-based digital signature standard, and key encapsulation mechanisms. Our attacks range from digital signature to key exchange, from classical to post-content cryptography. If you are interested in how they are going to work out, please check out paper. GoFetch has real-world impact. As a response to GoFetch, Apple released a guidance of enabling data-independent timing bits for constant-time cryptographic operations. Currently, this bit can only disable DMP on Apple M3 processors and perhaps newer generation of Apple silicons, but not for M1 and M2. Go is planning to add an opt-in DIT bit in its binary to let their user to determine if they have such a concern and want to take extra precaution. Also, by the way, GoFetch was presented at CoffConf this year. Please see the picture. Marken, the leader of Asahi Linux project, found the chicken bit to disable DMP on Apple M1 and M2 chips. But this bit can only be set in the kernel space. According to Marken's Mastodon post, he will write up a patch for this. Last but not least, GoFetch is announced as the best cryptographic attacks winner by Ponyworld this year. Finally, we conclude that the DMP performs secret-dependent memory access to leak the data, and exploiting the DMP to perform key extraction attacks against constant-time cryptographic implementation is feasible. Please check out website, and thanks for listening.